Today, we are diving into something called flash attention. And I know it sounds technical, but trust me, it's one of the key reasons the AI we use every day is getting so much faster and so much more powerful. Let's get right into it.
I mean, you've seen it, right? These large language models can write code, they can come up with poetry, they can summarize these massive, complex documents in just a few seconds. It's honestly kind of mind-blowing how fast their capabilities are growing.
But there's a catch. Underneath all that incredible power, there's a fundamental weakness, a bottleneck that has been holding them back, capping just how much information these AIs can actually handle at one time.
Seriously, think about it. Why can an AI summarize a 10-page report like it's nothing? But if you try to feed it an entire novel, it just chokes? What's the invisible wall here? Well, the answer is all about memory.
So that brings us right to the heart of the issue. There's this thing called the attention mechanism. It's the secret sauce that lets a model understand context, how words relate to each other. But it comes at a truly staggering cost.
Okay, so here's the deal. For an AI to get the context, it has to look at every single word and compare it to every other single word in the text. Now, for a short sentence, that's fine. But here's the kicker. If you double the amount of text, you don't just double the work, you quadruple it. This is what's called quadratic complexity, and it means the workload just absolutely explodes as the text gets longer. Now, your first thought might be, okay, so we just need more raw processing power, right? Faster computers. But here's the plot twist. The real bottleneck isn't the number of calculations, it's something way more basic. Yeah, you heard that right. The problem isn't doing the math, it's moving the data around. A GPU can crunch numbers at lightning speed, but it turns out it spends most of its time just sitting there, waiting for data to get shuttled in from memory. It's like the commute to work is way longer than the workday itself. And this image explains why perfectly. A GPU has two different kinds of memory. Just think of it like a workshop. You've got a small workbench right in front of you. That's called SRAM. It is incredibly fast, but it's tiny. Then you've got this massive warehouse out back. That's HBM. It can store a ton of stuff, but every single trip to go fetch something, well, that takes a lot of precious time. And when I say the speed difference is big, I mean it's staggering. That fast little SRAM workbench, it moves data at 19 terabytes a second, but it can only hold about 20 megabytes. The huge HBM warehouse holds 40 gigabytes, tons of space, but it's over 10 times slower, at just 1.5 terabytes per second. The old way of doing things forced constant, slow, painful trips to that warehouse. And this whole problem is only getting worse. Look at this chart. Over the last 2 decades, our processing power, the speed of our tools on the workbench, has gotten 60,000 times faster. But the speed of getting things from the warehouse, that's only improved by 100 times. This massive widening gap is what engineers call the memory wall. So if we can't make the warehouse faster, what do we do? Well, the answer isn't to work harder, it's to work smarter. And this is exactly where flash attention comes in, with a totally different game plan. The core idea has a technical name, I/O awareness. But the concept is actually really simple. It means redesigning the whole process with one main goal. Make as few trips to that slow warehouse as possible. It's like planning your project perfectly, so you only have to go to the warehouse once to get everything you need for the whole day. So how in the world does flash attention actually pull this off? It uses two really clever tactics that completely change the way the work gets done. The whole strategy boils down to these two clever tricks, tiling and recomputation. So let's break down how each one helps keep the processor humming along, instead of waiting for those slow deliveries from the memory warehouse. First step is tiling. So on the left, you see that huge, scary attention matrix. It's way, way too big for our fast little SRAM workbench. Now look at the right. Flash attention just chops that monster problem into smaller, manageable blocks, or tiles. Each tile is small enough to fit entirely on the workbench. So you load a tile, do all the math you need to do right there, and only write the final answer back to the warehouse when you're completely done. The second tactic is recomputation, and this is where it gets really brilliant. It's a trade-off. See, normally you have to save all these intermediate calculations in that slow warehouse memory. Flash attention's philosophy is basically forget that. Accessing memory is the bottleneck, not the math. So it just recalculates those little steps on the fly whenever it needs them. It's a little bit of extra math in exchange for avoiding a ton of slow trips to the warehouse.
So, what's the big payoff for all this cleverness? Well, the results are nothing short of dramatic, leading to AI that's not just faster, but way more capable.
Just get a load of these numbers. With a standard method, a single operation meant shuffling over 40 gigabytes of data back and forth from the slow HPM warehouse. With flash attention, it's just 4.4 gigabytes. That is a nearly 10 times reduction in memory traffic. And the result? The runtime just plummets from almost 42 milliseconds down to just 7. And that speed up has a massive real-world impact. This chart here shows the training speed up for a GPT-2 model. Flash attention makes it 3.5 times faster. In the real world, that can mean cutting the training time for a new AI model from 3 weeks down to just 1. For developers, that is a huge, huge deal. But this is where it gets even cooler. It's not just about speed. It's about unlocking brand new capabilities. Here, you see different models trying to process a long document, 8,000 words. The standard methods just crash. They literally run out of memory. But flash attention? It handles it no problem. It's not just making AI faster. It's letting AI do things that were physically impossible before. So, flash attention completely revolutionized training these giant models. But that's only half the story. What happens when we actually want to use them, to ask a question? That whole process, which is called inference, has its own unique set of challenges.
And that's where its sequel, Flash-Decoding, comes into play. It takes the exact same brilliant I/O-aware ideas, minimizing those slow memory trips, and applies them to the process of generating an answer. This is what makes it faster for you, the user, to get that summary of the entire book we were talking about at the start.
At the end of the day, the breakthrough of flash attention wasn't just a clever algorithm. It was a completely new way of thinking about the problem. It proved that sometimes the biggest barriers aren't about having more raw power, but about being smarter with the power you already have. It really makes you wonder, doesn't it? What other walls in AI are just waiting for a similar shift in perspective to come tumbling down?